CCI, Crash Course Instrumentation, presents Episode number 70. Reduce, Solve, Expand, the Playbook in Action. Hook. Can you find every voltage and current in a mixed circuit using nothing but plain English and a few round numbers? Let's run the full playbook start to finish. No bench, no calculator gymnastics. Roadmap. We will set up one tidy combo circuit in words, collapse it to a single equivalent, get the total current, expand back to each part, and finish with two quick checks. Set up in words, round numbers for mental math. Picture a battery feeding 3 resistors arranged like this: a single resistor called A, followed by a parallel pair called B and C. That means A is in series with the parallel block of B and C. Give them friendly values. A is 200 ohms, B is 400 ohms, C is 400 ohms. The source is 24 volts. The numbers are chosen so you can feel the ratios without grinding. Reduce to an equivalent. First, collapse the parallel pair. Because B and C are equal and in parallel, their equivalent is half of one of them. Half of 400 ohms is 200 ohms. Now notice A is in series with that equivalent. Series resistances add, so the total seen by the source is 200 plus 200, which is 400 ohms. Solve the total. With 24 volts across 400 ohms, the total current from the source is 24 divided by 400. In easy fractions, that is roughly 0.06 amps, also called 60 milliamps. Expand step 1. Series block back to A and the parallel block. Series shares current, so the same 60 milliamps flows through resistor A and then into the parallel junction. The voltage drop across A is current times resistance. 60 milliamps times 200 ohms gives about 12 volts. That leaves about 12 volts for the rest of the circuit, which must be the voltage across the entire parallel block. Expand step 2. Inside the parallel pair. Parallel shares voltage, so both B and C each see the same 12 volts across their ends. The current in each branch is that 12 volts divided by 400 ohms, which is about 30 milliamps in B and 30 milliamps in C. Those two branch currents add back up to the 60 milliamps we sent in, which is exactly what we expect at a node. Checks that take seconds. Loop check, KVL. Source rise of 24 volts equals drop of about 12 volts across A, plus drop of about 12 volts across the parallel block. The sum is 0 around the loop, so the arithmetic is consistent. Node check, KCL. 60 milliamps arrives at the junction, splits into 30 and 30, and then reunites to 60. In equals out, so the node balances. Why this example teaches the general rule. We collapsed parallel first because it was obvious. Then we added the series piece. That order is not a law. Any clearly isolated series or parallel chunk can go first, but starting with the most obvious reduction simplifies the rest. Notice the transfer rules used during expansion. Current copies through series sections, voltage copies across parallel sections. Everything else is a quick Ohm's law fill-in. What to do when the numbers are not friendly? Keep the same flow. Reduce to an equivalent, compute the total, expand while copying the shared quantity, and fill remaining values. If values are awkward, estimate to check direction and magnitude before you reach for precise tools. If a current source or a dependent element appears, mark what is given first. For a current source, the branch current is fixed, and the simulator or math finds the resulting voltage. For a voltage source, the branch voltage is fixed, and the resulting current follows from the surrounding resistance. Recap you can say out loud. Series shares current. Parallel shares voltage. Reduce obvious groups. Find the total. Expand and copy the shared quantity. Check one loop and one node. If both checks pass, you own the circuit. Thanks to Tony Kuphaldt and the open source community for the Mod-L project. If this helped, like and subscribe to Crash Course Instrumentation, then roll into episode 71, where we use a VARP table to keep everything organized on one page.